Good morning, everyone from Sweden. It's a pleasure to have you with us in this webinar. My name is Ehsan Ghasemali, and it's a pleasure to be your host today for this webinar with the title of Light Metal Surface Treatment for Extreme Conditions, focusing on plasma electrolytic oxidation. It is a webinar within the Webland project in which almost every 2 weeks, we have a webinar related to metal and polymer component manufacturing. It is webinar number 29 within the Webland project. We had around 33 participants or registrants in this webinar. From more than 6 countries, as you see in the list. It's a pleasure to have you with us from both university, academia, and also non-academic sector. And it's a pleasure to see a quite international audience in our webinar, as usual we have in almost in all our webinars. As I said, this webinar is a part of a WebLearn project in which every 2 weeks we have a webinar dedicated to various topics related to metal and polymer component manufacturing. You can read more about this project in the web page that is mentioned in the website, ju.se/weblearn. And it's a project that will be conducted for 2 years, but we plan to continue even after the end of the project, after the support that we are receiving from KK Stiftelsen or Knowledge Foundation, as a funding agency in Sweden. It's a pleasure to receive the fund from those from this funding agency, and all the topics that we are conducting for, the webinar for in this project has been developed together with industry, at least in Sweden, and also international industrial partners, or based on the needs that industry has. You see the moderators for the webinar today, myself and Maximilian Sieber, my colleague at the School of Engineering, Jönköping University. But more importantly, Frank Simchen is our honorary guest today as a lecturer for the webinar that will present very interesting research outcome related to the topic that we mentioned from Technical University in Chemnitz in Germany. It's a pleasure to have you with us, Frank. A very summary version of the agenda. After this short introduction, we will have the main part, which is webinar presentation, which will follow up with some discussion. So in our webinars, we would like to have more interaction to avoid just one-way information sharing, making sure that there's more interaction, both for networking and also sharing the knowledge and discussing the topic further. We hope to wrap up the webinar within 1.5 hours from now. Some technicalities, we would be grateful if you turn off your microphone or mute your microphone. Questions are more than welcome, but please raise them in the chat function in Zoom, and we will answer them either at the end of the presentation or whenever there's opportunity to discuss the questions in the chat. Group discussion or panel discussion that we will have in the webinar is a very important part of our webinars, as I mentioned, and you're more than welcome to participate in this panel discussion with your questions, or if you have any idea to discuss the questions that are raised by others. We will record all our webinars, and afterwards you will receive the presentation, the PowerPoint, as well as the recording. So please turn off your camera in case you don't want your picture to be in the recorded version of the webinar. We will not share the group discussion or the panel discussion at the end of the webinar. So for that part, you're more than welcome to unmute yourself or turn on your video in case you want to be engaged more lively in the discussion. For those who are not aware or familiar with Zoom, I think we are all, thanks to pandemic, we are all aware of what is Zoom and how it works. But in case you are not familiar with that, you see the functions on the slide. On the left side, you can see where you can mute and unmute your microphone, turn on and turn off your camera, and also the chat function in which you can send your questions either to myself Ehsan, or send it to everyone. And whenever there's an opportunity, we will ask the questions from the presenters. So that was from my side. Very looking forward to see your presentation, Frank. The scene is yours.
Okay. Okay. Thanks for the nice introduction. Since everything has been told, I want to start directly with my presentation. The report is divided into two parts. Firstly, we will classify the PEO process within the related anodic coating processes, and then deal with the actual PEO process nature. Afterwards, we will speak about typical coating characteristics and discuss some practical applications of the method using concrete examples. So when we speak about the anodic surface technology in general, they have one into common. We place our metallic material into a suitable aqueous electrolyte and apply a positive polarization. That's why it's called anodizing. And this positive polarization leads to the fact that we take electrons out of the metallic lattice. The metallic atoms are turned into ions and react with the electrolyte in order to form an oxidic coating. And in case that we are using non-dissolving electrolytes, so electrolytes which cannot attack the oxide itself, and apply voltages between 1 and 200 volts, we carry out so-called barrier layer anodizing, which we can know from interference coloring of titanium substrates, or example for manufacturing electrolyte capacitors. In case that we are using electrolytes like sulfuric acid, which can attack the already formed aluminum oxide, we carry out this method, which the most people think about when they listen to process anodizing, the conventional DC anodizing of aluminum in sulfuric acid. And depending on the electrolyte temperature, we carry out anodizing or hot anodizing with different oxide volume of this common regular cell structure. And yeah, our coating range is in between 20 and 30 micrometers, maybe a little bit more in special applications. And our voltage can rise up to 50 volt. And if we apply much higher voltages, interesting plasma electrolytical reactions come into play and lead to the formation of plasma electrolytic spark discharges, which form, in case that the process is balanced well, the oxide ceramic coating, which will be part of this, will be focus of this presentation. So, but what actually happens? What actually happens during PO? On this slide, I have summarized a simplified explanation. Our working piece is placed into an passivating electrolyte and receives the alternating polarization. And during the anodic half cycle, the various electrochemical and plasma chemical sub-processes take place, which I will mention here based on a schematic representation of the sample and an exemplary current density potential curve. So first of all, we have our naked working piece. Then we apply the first step of polarization, and this leads to the formation of an electrical isolating reaction layer, the so-called passive film. And if we elevate the voltage more, the increasing what is the word? The increasing space charge leads to the formation of a gaseous film which surrounds the working piece. And the interface between the gaseous zone around the working piece and the bulk electrolyte is getting an area of equal electrical potential, the so-called quasi-cathode. And afterwards, this quasi-cathode is getting the origin of plasma electrolytic spark discharges, which strike from the electrolyte into the substrate and form an oxide ceramic coating. So this discharge phenomena are leading to oxide formation, incorporation of electrolyte components, and melting and remelting of already formed oxide. And this process nature also causes an excellent geometric freeing power. In context of wet chemical coating methods, this means with this process, we can apply coatings on components which have a really complicated geometry. So if you think about metal deposition, you apply a metal conductive coating material. You apply an electrical conductive coating material on an electrical conductive substrate. So the field lines don't have any reason to go behind undercuts and inside of drillings maybe. So the throwing power is not so perfect. But when you apply a polarization of maybe 500 volts, and in some regions of your components, you have electrical isolating oxide, and in our regions, you have still naked metal, the discharges have reason to appear there. So you can apply a coating on geometries which are really complicated. So, and the method is called plasma electrolytic oxidation, because of the discharges are indeed of plasmatic nature. So the core of every plasma electrolytic discharge is hotter than the surface of our sun. And this causes a lot of interesting mechanisms, which I cannot explain because I'm just an engineer, but they also lead to an interesting aspect, which I want to explain on this slide, and based on the discharge model of Mikhailo Klapkev. So we see here our metal anode, our already formed oxide, our electrolyte, and here close to the substrate electrolyte interface, the quasi-cathode. And then we apply our polarization and we got our plasma channel. So here inside the oxide, we have a plasmatic zone. And in this zone, we will find substrate constituents and electrolyte constituents. And around this plasma channel, we find different zones of evaporated oxide and molten oxide. On the electrolyte side, a zone of thermical dissociated electrolyte components. And around the plasma channel, an area where polymorphic fast transformations take place. So inside we have really hot plasma and outside molten oxide, and here a zone of gaseous oxide. We apply an alternating electrochemical pulse. So this discharges appear and collapsing and appear and collapsing. And in this area of polymorphic transformation, there takes place a transformation of amorphous aluminum oxide into crystalline aluminum oxide. So the electrochemically formed reaction layer from the passivating step consists in amorphous aluminum oxide. And step by step appear these discharges and transfer this amorphous oxide into crystalline oxide. And if we consider maybe carbon, we know that crystalline carbon diamond is much harder than amorphous carbon like graphite. And with aluminum oxide, it's something in that way. This crystalline aluminum oxide is much harder and resistant than amorphous aluminum oxide and leads to a better wear protection. And this melting, remelting, and quenching reactions are influenced by practically all process parameters, by the electrolyte composition, the applied pulse, and also the substrate. So here we see a nice example of aluminum substrates which were treated by PAO under constant conditions regarding electrolyte and electrical regime. But we see here in dependency of the chosen substrate alloy, we get completely different distribution of the appearing oxide modifications. So we have here the conventional crystal aluminum oxide, and the green phase is corundum, which is a very hard oxide modification. So this is just an interesting aspect to know, which really separates plasma electrolytic oxidation from the conventional anodizing methods. We create a high amount of crystalline aluminum oxide modifications. Okay. So here, let's take a look on a short video clip where we see that the process is not just useful, it's also pretty. We see here development of the spark discharges with elevated speed. And on the right side, we see an SEM micrograph of the resulting layer structure, and on the left side of it, a schematic representation. So we have our metallic substrate. Over the metallic substrate, a thin reaction layer. So the electrochemically formed barrier layer is still visible in the or still detectable in the resulting coating, because with every spark discharge or with any alternating of the pulse, we create a new amorphous barrier layer, but it's just in a scale of some nanometers. So this you will not see here directly into the SEM graph. And over this barrier layer, we find an area of very dense oxide material, the so-called walking layer, which offers the most real protection. And over the walking layer, we find a region with a higher porosity, the so-called technological layer, which you can use, for example, to apply some color or any maybe Teflon, any another additives. This technological layer offers a good substrate bonding to further resin or color or what you want to apply on it. And inside the dense oxide structure, you find some remaining porosity, some discharge channels and cracks, and also some closed pores. And just to show that we have to deal with a really dense oxide morphology, we have here an exemplary series of grinding pictures. We took such a coating and grinded step by step. Firstly, we see an untreated top view, and after we see how the morphology develops if we go 3, 12, 18, and 25 micrometers inside the coating. And we see that we have a really dense oxide morphology. So, and these coatings can be thicker than 100 micrometers, and we can achieve hardnesses of around 2000 Vickers values. So this you will not get by conventional anodizing. We have a very good substrate bonding due to atomic bonds. So this oxide is connected to the substrate really by atomic bonds. So we have a very, very good substrate adhesion, and we can get a compact morphology, but just after a certain process time. So this compacting of this oxide layer just takes place after a certain time of melting and remelting the oxide. So to get a compact layer of just 20 or 30 micrometers is not possible, or at least it's not so easy. Just with 50, 60 micrometers thicknesses, these coatings start to be really dense and protective. And this we can discuss here on the slide regarding the coating characteristics. Here we see an example. We applied a rubber reel test on a PO coating, which was formed on such aluminum magnesium silicon alloy. And usually this rubber reel test is a really challenging wear test, but we see that we carried out rather polishing. We removed the outer porous part, and the inside working layer of the PO coating is basically unaffected. So we carried out a rather polishing step than that we create any significant rear result. And if we speak about the corrosion resistance of such a PO coatings, they offer good corrosion protection, but especially when you are acting with aqueous or liquid corrosive media, it's recommended to apply an additional sealing step. And this is related to the morphology of the coatings. Of course, this crystalline aluminum oxide itself is very resistant against chemical attack, but we have to deal with the intrinsic crack structure. So if you place this component at longer time into any aqueous media, it's possible that the corrosive components can come through the micro crack network until the substrate. And then we have a substrate material of low electrochemical standard potential. And here any long crack and any corrosive media. And these are perfect and excellent conditions for pitting corrosion, and that's why it's recommended to apply any sealing step afterwards. For this, you can use any polymeric resin or, for example, salt shield systems. And now let's speak about fatigue wear. Here it needs to be stated that PO coatings are sensitive to be damaged by continuous alternating mechanical stresses, which is caused basically by the ceramic nature of the applied coating. And we know ceramics are brittle and tend to crack. And if such a crack starts to grow, the excellent substrate bonding of the coating supports a transmission of the crack into the substrate. And that's why we see here on an exemplary Wheeler curve of an PO-coated substrate. We see here in this Wheeler curve that the Wheeler curve of the PO-coated substrate is significantly below the untreated substrate. So this is a challenge which we have to deal. The theory behind is much more complicated. Their residual stresses also play a significant role. And for further details, I recommend the literature of Lisa Winter, who is my co-worker and wrote her PhD project about this topic. And yeah, regarding the sealing, I want to say that we are working in our working group for a process to apply an in situ sealing step within the PO electrolyte. So we create a PO coating, and after this component stays inside the electrolyte and we change the alternating electrical regime, play with some pH shifts which occur there, and then we apply the sealing in situ. So after you take the component out of the bath, you have your formed PO coating, and you also got your sealing, which closed the remaining pores. We have received funding for 2 research projects. One thing is HCF anode. And in this project, we focus about the interaction of the PO process parameters, the created residual stresses, and the resulting fatigue behavior. And we now just start with another research project where we focus to reinforce the created aluminum oxide coating with zirconium oxide to get a composite ceramic material with an elevated crack fracture toughness. So we want to stop the formation of the crack inside the coating and so improve the fatigue behavior of these components. So, but I also want to state that the sensitivity against fatigue is just a fact which should be taken into account. And it's not an exclusion criterion, because if you decide your component well, then you can use PO coatings also in applications of strongly alternating mechanical stresses. And here we come to our first application. This is the rotor of an topiomolecular pump, which is used in ship industry to transport corrosive gases. And this topiomolecular pump is turning with some 10,000 rounds per minute. So it's really fast. And such a component should be not so heavy, just to keep sure that they are not jumping anytime outside of your system. And if you transport corrosive etching gases like in ship industry or in semiconductor industry, hydrofluoric gas, then that's also a big challenge for the corrosion protection. And with PO coatings, you can fulfill this request. So the substrate is not heavy because it's done from aluminum. The coating is not heavy because it's done from aluminum oxide. The coating offers a good resistance against the against the corrosive stresses. And we have to deal here with an unbelievably complicated substrate geometry. So there are other methods for applying oxide ceramic coatings, for example, thermal spraying, but it will be not so easy to apply on this component any thermal spray coating. But with PO, you really can deal with this complicated component geometry. So you can go here behind all these undercuts. And on the right side, we see a sound speaker. This is a component of high quality sound systems, which are used at expensive cars, for example. And this is done from magnesium. Magnesium is much stiffer than, for example, polymeric materials, has a better acoustic damping behavior than the most of other metals, and can be produced by investment casting with very thin walls. And so magnesium is here really the material of choice for such a sound treater. And in order to provide any decorative coating and to prevent corrosion in use, here's applied PO coating. And by the way, we see here the PO can be also used to color components, for example, to blacken it here. Maybe it was done by vanadium oxide, at least these components I read often in publication when somebody write publications about blackening components by plasma electrolytic oxidation. Some colors are also known in literature. From my point of view, black color could be the only one which is carried out commercially. until now. Okay. On the next slide, we see some another interesting applications from the company of Innovent, which is located in the town of Jena in our closer neighborhood. And first of all, we see here the greenhouse of the International Space Station. So in the background, you see our planet. And here in front, you see the housing of a device for astrobiological experiments, where our astronauts and cosmonauts try to plant space vegetables in order to provide people there on the station anytime with self-grown food. And yeah, these housing components are here provided with PO coatings. Firstly of all, to offer suitable corrosion protection. And secondly, it's very important in space engineering to apply coatings with an excellent thermocycle behavior. So when the International Space Station is turning around the planet, these components here receive high changes in temperature. If they're on backside of the Earth and they don't see the sun, they are getting very cold. And when they are confronted directly to sun, they can heat up really strong. We must consider in space, we are in vacuum, so we don't have a heat transport by convection. We don't have heat transport by conduction. We just have heat transport by radiation. So we can receive here strong changes in heat. And a lot of other coatings could flag off during use time. And we also cannot fly there so easy to change these components. So that's why PO is here the coating process of choice. Here we see another component from space technology, a housing of optical devices. This housing is blackened in order to prevent spoiling of the detected optical data by any reflections of the component. And also this device should not heat up in use. To this answer, I will answer this question. I will answer later. So yeah, this component should not heat up. That is also one reason to blacken it, because we still can use the radiation mechanism to get a suitable thermal balancing of this component. Here we have a medical device which is placed in your body to repair any bone fracture. So this titanium compound is provided with a titanium oxide layer through PEO in order to prevent cold welding. When you apply here any titanium screw inside, and this components can get cold welding over time in your body. And after you want to deconnect these components, and then it's not so easy to deconnect the screw. That's why it's good to have here a thick titanium oxide layer. And here we see an aluminum heat sink, and we see you have here really long channels. It would be not so easy to apply the oxide ceramic coating here inside the channel. And that's why PEO is the process of choice. So here we have some more applications from medical issues done by the German company Meotech. Here we have one implantat which is placed into your body. The best implantat is this one, which you don't need to remove after the operation. So you have this magnesium component inside your body. It fulfills any function. And then when your bone is good again, you maybe want to prevent to make a second operation to move the component outside. And the human body can degrade magnesium components over some months. So you can place it inside, and after some months, it will be removed by your own body. But maybe you need this component 30 months inside, and after 24 months, your body transports this component away. So you can apply a magnesium oxide coatings via PEO in order to adjust the degradation time. So this is one use of medical engineering. The same stuff is done here with a stent, which is planted inside of a human heart to elevate such a blood vase for a certain time. And since I'm by myself a little bit over speaking time, these are so-called scan body locators. The application is a little bit more complicated. For this, I want to refer to this one publication, what is referred here by this indication. So with these statements, I want to finish the first part of my presentation. by the way, make a little bit advertisement for a special issue in the Coatings Journal, which is edited by my co-worker, Dr. Morgenstern, and me. And I'm now prepared to answer to some questions which received in the chat and maybe come from Dr. Sivo.
Yeah, thank you, Frank, for this very nice presentation. So first question we have, is the fatigue reduction valid also for castings that have much higher density and size of defects and larger microstructural phases than extrusions? So we are talking about order of magnitude of damages in the substrate itself, comparing casting and wrought alloys compared to the coating.
Let's say fatigue is never good. Of course, this is what I wanted to say when I said it's a challenge which need to be taken into account when you design the component. This topiomolecular pump is working very well over years of process time, and it's done by casted aluminum silicon alloy. You should prevent too thin components. The crack could start anytime from the coating, but if the component is big and stiff enough, you will delay such reactions. So it's not automatically every component which is treated by PEO will be broken after by fatigue. You just should take it into account when you design components with really thin wall thicknesses and in really demanding applications. So.
Okay, thank you. Then we have another question, which is about the gas permeation, for example, hydrogen performance of these coatings. You already mentioned the application in this turbomolecular pump. Can you give us an idea about that gas permeation performance?
Gas permeation. It's possible that the gas comes through the coating to the substrate because it's a little bit like thermal spray coating. You still have your crack network. That's why you're using a FOFA sealing step. Such a FOFA sealing step was also used by producing this topiomolecular pump. And I'm not sure if the question was motivated in this direction, especially when you transport such each gases which don't need to be contaminated by any component. It's also important that the coating don't release any gases. Yeah, this is also important for these optical devices which are showed there for space engineering. The ceramic coating don't release any gases. So the outgassing value, which is controlled in some challenging applications, is very, very low at PO coatings. So you don't contaminate any optical devices by outgassing of the PO. You don't contaminate your etching gases by use of this topiomolecular pump. And yeah, this is also one interesting aspect of this coating. With this gas permeation, if there's any question more in detail, maybe I can receive one mail from you and we can discuss this application or this challenge in detail.
Okay, thank you. One more question is about the residual stresses that you mentioned shortly. So can you say in general which type of residual stresses we have in the PEO coating, and then also maybe compare them to like the anodized coatings?
We are more people in our working group, and especially this residual stresses is not my main part. For this question, Dr. Winter would be able to answer really perfect. And also it would be good to read her literature. But this is also one question which I will take to answer later per mail. I think inside the coating, this we have pressure tension, so positive tension. And inside the substrate, we have negative tension. So it's stresses in this way. So the interaction of the residual stresses is in that way that they are really suitable to start a beginning of cracking. This I can say now. It's not a satisfying answer, but we will be able to answer to this question in detail. Please write me a mail. I have really one expert sitting in the next office who can explain it really in detail.
Okay, thank you. And then maybe one last question before you continue with the second part of your presentation. You talked about remelting of the oxide itself, is there any danger of damaging the substrate by those thermal effects?
No, this is I learned plasma anodizing from Dr. Sieber, and I remember when I was a student, I was shocked when he took the component after the process outside the bath and touched it by hand, because after I saw there 1 hour this plasma discharges, I was sure that the component is hot, and maybe it's hand warm. So maybe you have a tiny thermal influence zone below the layer, but it's really tiny. It's not detectable with easy methods. So you don't, for example, you don't need to be scared that you change the Wärmebehandlungszustand,
The heat treatment state.
The heat treatment state, yeah. So if you put an T6 aluminum alloy and apply this coating, afterwards you still have a T6 aluminum alloy. So the thermal influence to the substrate is maybe exists, maybe detectable with scientific methods, but it doesn't play a role in this technological scale. It's there. This discharges are unbelievable hot and unbelievable tiny. So this leads to the funny result.
Okay, thank you. So I would say we are looking forward to the second part of your presentation, where you will talk a little bit more about recent results from your research and development.
Yeah. So we spoke a little bit about the process nature, the coating characteristics, and the applications. And now on the next slide, I want to present some, let's call it scientific methods, which we are using to design a PAO process on new substrates, and also which kind of process diagnostics we developed in order to look inside the process, what we already did and what are our next steps. And on the last slide, I want to give a short outlook, what can happen in future at our institute, and maybe an interaction with the people who are listening now. So first of all, I told that the initial step doing plasma anodizing is passivation. This is a really critical, important step, because basically there are 3 anodic reactions in competition when you apply anodic polarization to a metallic substrate. Of course, it's a strong simplification, but it can help you to categorize your problems. So if you apply anodic polarization to a metallic substrate, you can get metal dissolution. Yeah. So just metal atoms turn into metal ions and they go into liquid state and fly away. This is when you have a dissolving anode, or if the electrolyte substrate system is dissolving. You also can create electrolysis, which you use, for example, if you want to produce hydrogen and oxygen. And on the anode, this is combined every time by oxygen formation and hydrogen development of hydrogen ions. So you get a local pH drop. And if in case that you chose a suitable electrolyte, this will lead to the formation of an electrically isolating reaction layer. So your metal ion reacts with the electrolyte to form any oxide. And in best case, this metal oxide is electrically isolating. So, but if this metal oxide is electrically isolating, it's not the only request which must be fulfilled. The volume of the reaction product must be also in a suitable range to the substrate metal. So this relation was firstly scientifically described by Pilling and Bedroof by 2 scientists. They create a so-called Pilling-Bedroof ratio, which should be here in R, not in V, because in Germany it's Pilling-Bedroof-Verhältnis. And if in case that the volume of the oxide and the volume of the metal is in an unsuitable range below 0, you have you get your electrical isolating oxide, but you don't get a dense oxide layer. You get anything where permanently appear any cracks. And in case that they are in suitable range, between 1 and 2, you get an oxide which completely colloses your metallic surface. And if this ratio is too high, for example, in case of iron and iron oxide, you will create your oxidic layer, but this oxidic layer will flag off permanently. And this system will be also not electrical isolating. And this is really important in PAO. And in PAO, we don't working in atmospheric conditions. We are working in aqueous conditions. That's why Mr. Song created, just extended this idea to aqueous environment to define the product metal ratio, which follows the same idea. And this offers you geometrically boundary conditions for forming a good, stable electrical isolating reaction layer. So that's about the main model. Now it's good if you are able to simulate such stuff before you prepare 10 liters of electrolytes to find out that the system is not working. And another scientist, Marcel Probet, gave us one interesting tool to give an electrochemical prediction about the passivation behavior of a certain electrolyte metal combinations, the so-called potential pH diagrams, which are also called often Probet diagrams. And looking here, for example, in that way for magnesium and aluminum. So you have here any statement about stability regions of magnesium of your metallic substrate in dependency of the pH level and applied potential. So for example, magnesium, you would say in an alkaline range, the substrate could be stable because you form magnesium hydroxide, and in neutral to acidly range, you will get corrosion because magnesium ions just shifted away. Aluminium, you have your stability range in a neutral region, and in acidly and alkaline environment, you also will not get any passivation. And if you then think about how to adjust such systems or to simulate electrolyte substrate combinations, you can use superior software from Sweden by using equilibrium diagrams using sophisticated algorithms. The Medusa software package from the University of Stockholm. This is an open source software tool, which is really powerful and easy from my point of view. There exists also some commercial softwares for this challenge. One of them is, for example, Thermocalc. And there you can say, okay, the most electrolytes which are used for the PO of aluminum, they are alkaline silicate solutions. And we see here, if we apply some silicate, sodium silicate to our electrolyte, we see that the stability regions of aluminum are extended in alkaline direction. So, of course, these diagrams just consider thermodynamic applications and don't respect any kinetic limitations. And what is more challenging, they finished at 5 volt, and in PEO we go up to 500 volt. So, and theory also doesn't help so often. So we need also any experimental method, and we still don't want to prepare every time 10 liters of electrolytes before we start an experiment and find out the system is not working. So that's why we develop an electrochemical method, which we are using to pre-select suitable electrolyte substrate combinations. We apply here our metallic sample below an electrochemical cell, have here a sealing ring, and here a really low electrolyte volume of maybe 250 milliliters. We are working in 3 electrode arrangement. So our component, our sample is the working electrode. We have a counter electrode by platinum, and in the middle our reference electrode. And now we apply a special potential cycle. So we go from 0 to 100 volt within, we go from 0 to 100 volt within 100 seconds. And then we can see if we have anodic metal dissolution and electrolysis, or we have passive layer formation. Because in case that we have anodic metal dissolution or anodic oxide formation, just at a low voltage value, we will come to the point that the current flow is too high for the experimental setup and the process is stopped. So maybe here at 12 volt, anodic metal dissolution was dominating, passivation didn't take place, and the process was stopping. If we improve our electrolyte, then step by step, maybe we can go to 60 volt, to 80 volt, to 100 volt. And anytime our passivation is good enough that we can carry out the complete measurement, and we can record the corresponding current flow. So we have here our voltage ramp. Initially, we have our naked metal, so we have an initial active peak. Then the formation of the passive layer takes place. The electrical resistance is increasing, so we have a lower current flow. And then step by step, the current is rising over the measurement time. and and we integrate the flowing charge, the flowing current over a certain time of this measure of this experiment, and get such a characteristic sigma value. And this helps us for the determination of comparable characteristic values. So if the passivation is bad, we just achieve here this breakthrough voltage. If the passivation is better, we get a sigma value. And then step by step, if the passivation is getting better and better, the current flow is getting lower and the sigma value is getting lower also. So you can, in one afternoon, you can test, depending how fast you are, 10 electrolyte combinations in your setup. You just need a low amount of electrolyte and you can pre-select your electrolytes really fast. Okay, but then we come still in the situation that we have any input parameters, substrate, electrolyte, and electrical pulse. Then we apply 1 hour of plasma discharges and our components or all these substances are catapulted from solid to liquid to gas to plasma and back 100 times per second, within some milliseconds. And after 1 hour, we receive any coating, and now we need to understand what happened here. So we have some input parameters, 1 hour of chaos, and then we get any result. And this is sometimes frustrating to create any story what happens in this 1 hour of chaos, just based on metallographic methods. That's why we developed a setup for process diagnostics. And here I firstly ask you to take into account the development of direct electrical resistance during the PEO process. In conventional electroplating, galvanic processes, you apply electrical conductive metal on another electrical conductive metal, so the resistance is not changing. In conventional anodizing, you apply aluminum oxide coatings on aluminum, but this aluminum oxide coating is still filled with pores, and the pores are filled with sulfuric acid, so the resistance is not increasing strong. But doing PEO, you create 50 or 100 micrometers of crystalline oxide, and you have here some channels to the electrical active interface zone. So here take place a lot of interesting electrochemical subprocesses, and they all interact with the electrical pulse. And this we see when in case that we measure our electrical parameters. So maybe we define a rectangular pulse, but this rectangular pulse leads to a PO coating with certain characteristics, with a certain thickness and porosity. And they, again, interact with the rectifier controlling behavior, which is the most undervalued input parameter of your system, because usually you don't know by yourself how is the rectifier controlling behavior. The company who built this rectifier will not tell it to you. And so the thickness, porosity, and resistance of the coating influences the required voltage signal which you need for applying the predefined current signal. And that's why you can get a current signal which is completely different to this what you initially applied. And it's not a mistake of your rectifier. So our rectifier is working quite well, make really pretty rectangular pulses in non-passivating systems, or when we apply electrical conductive coatings. But if you apply PO coatings, you have a complicated interaction of all these parameters. So it didn't make it easy, it make it difficult to compare different experiments, and especially it's getting difficult to compare experiments of different working groups. But this interaction transports unbelievable a lot of informations and gives you experimental access to the stuff what happens during the process. And for this, we built up our experimental setup. So we define any electrical pulse, and then we measure directly the voltage signal over the electrodes and the current signal over a measurement resistor, which we placed in our setup. We placed a photodiode in front of the sample to get an additional integral information about the light formation. So with such a photodiode, costs 10, 15 euro. It's very cheap and you have a lot of fun with it because you get a lot of interesting information about which part of your pulse is electrochemical and which part of your pulse represents plasma chemical reactions. Because in every pulse, by every change of polarity of your component, you get new passivation, you get new space charge formation, and you get a new formation of a gas steam shell. And all these reactions are electrochemical. And then starts any spark discharges, and they are plasma chemical. So what of your parts is electrochemical and what's plasma chemical? And when you use this photodiode, you can get first access to this question, because everywhere where the photovoltage value is low, you have electrochemical reactions. So here we have the PEO of steel. So we have here an interesting electrochemical subprocess. And just when this voltage current characteristic is getting green, just in this case, we have to deal with plasma chemical reactions. I'm not sure if it's possible to see here the x-axis. I don't see it on my screen. So we have on this axis, we have the voltage, here's the current, and here we have the photovoltage. Okay, so we get, but from this photodiode, we just get integral informations regarding the spark intensity. And if we place additional camera, we get also informations regarding the spark distributions, which are also very interesting. And this is the current state of our experimental setup. It's not advertisement presentation, but I just want to relate to the companies Yokogawa Imaging and Plating Electronics. This company built our rectifier, and without the three companies, we would be not able to work. Yokogawa sold us our transient recorder, which we use to measure all the signals. And the company Imaging Solution is working together with us for our next step in process diagnostic. We incorporated a high-speed camera to make videos corresponding to our voltage or to the signals of our electrical process parameters. So we measure every 10 seconds for 100 milliseconds the electrical parameters. And the next step, we also want to film this 100 milliseconds, the process, to see what happens on the samples during we go through our pulse picture. And to improve the system, we also incorporate special measurement pulses, because the voltage shape is changing over the process time. That's why we incorporate measurement pulses with constant voltage forward feed to prevent the noise of some double layer capacitance effects. And we already received funding to incorporate an OES system inside of our setup. So soon we will be able to determine and investigate the chemical composition of the spark discharges which occur. And yeah, if you're working at university, you can be sometimes a little bit crazy, or also get ideas which maybe will not work so practically. But I would be really interested to place a pH optode directly to the component and to measure their pH shifts in range of some milliseconds. At the moment, everybody tell me it will not work. So we must see if we are able to make here a diagram more to see not just the electrical parameters, to see also any pH shifts, which are related to the passivating reaction and the competition of passivating and electrolysis, which is accompanied by gas development. So I'm nearly finished. I just want to give a short outlook, what in future can happen, or in future will happen in our working group. We are able to apply PEO not just on the standard so-called valve metals, we also can apply PEO on steel. And in this process, we can apply aluminum oxide coatings on steel substrate. So we were able to transfer the PEO, which is usually a conversion process, into a deposition method for ceramic materials. You can carry out PEO simultaneously on material compounds of different substrates, for example, here steel and aluminum. My PhD project is the identification of parasitic electrochemical subprocesses during the PEO of magnesium. So I hope in 1-2 years I can offer there some interesting results, but you can see here how different electrolyte additives influence the spark behavior. And we are also working for the PEO of completely new metals. Not just we go through the periodic system and look what is shining and what not. We also have a really innovative application for this in backhand. So maybe about this we will speak in future. We're working on materials which nobody else plasma anodized before us. And now we come to my last task to invite you to the coming capital of culture in Europe, Chemnitz, to our university, and maybe also to our institute. At our professor, we have here 3 working groups regarding chemical and electrochemical surface engineering. So I'm working at this working group, but we have also some smart co-workers in field of thermal coating and material characterization and development. So that's from my side, and I hope I will be able to answer to your questions.